Welcome to the deep dive, where we take complex topics, cut through the noise, and really try to distill the most important insights for you. Today, we're plunging into a truly fascinating and honestly increasingly critical area: the integration of edge computing within the Internet of Things, or IoT. For years, the cloud's been the sort of undisputed champion of data, hasn't it? We've all seen this incredible surge in connected devices. I mean, everything from the smart thermostats warming our homes to these intricate sensors buried deep within industrial machinery, all generating just an absolute avalanche of data, just tons of it. But here's where the landscape gets, well, truly intriguing. This data deluge, it's really pushing the limits of our traditional cloud-centric models. Because while the cloud is, no doubt, immensely powerful, it's not always the perfect fit when you need those real-time, instantaneous decisions right at the source of that information.
Exactly. That's precisely the shift we're going to unpack in this deep dive. We're looking at how edge computing is, well, fundamentally transforming data management, the analysis, and how we utilize data within these complex IoT environments. What's truly fascinating here, I think, is how it enables decisions to be made at, lightning speed. It drastically cuts down on latency by processing data precisely where it's generated,
Yeah.
rather than having to send every single bit and byte all the way back to some distant data center.
Right. So our mission today is really to give you a shortcut, a way to get exceptionally well informed on this crucial collaboration. We'll dive deep into its implications, and not just for the developers who are meticulously, building these complex systems, but also for the technical management folks who are charting these strategic courses for their organizations. By the end, you should have a much clearer picture of how organizations can steer their strategies towards solutions that are not just more efficient, but genuinely robust and crucially responsive IoT solutions. We'll explore the latest trends shaping this space, the practical challenges that definitely need to be overcome, and the immense opportunities that lie ahead in this incredibly dynamic landscape. Okay, so let's really unpack this term then, edge computing. It's a phrase that gets thrown around a lot, especially in tech circles. But what does it genuinely mean when we talk about it in the specific context of IoT? And maybe more importantly, how does it fundamentally diverge from that centralized cloud processing model that, let's be honest, most of us are so familiar with? Because, for many, the cloud is still the answer to everything.
That's a great question, and it really gets right to the heart of the matter. At its core, edge computing is basically about strategically moving computation and data storage geographically closer to the very sources generating that data. Think of it less as a replacement for the cloud that's a common misconception and more as a powerful extension, or maybe a deliberate distribution of processing power. So instead of every raw data stream, whether it's coming from a smart sensor on a factory floor or maybe a vehicle's onboard cameras or even your smart speaker at home, instead of all that having to travel potentially hundreds or thousands of miles to a centralized data center somewhere across the internet, edge computing processes some or all of that data right there at the edge of the network.
And this edge, it's not one specific place, is it? It could be different things.
Exactly. The edge isn't one fixed location. It could be the device itself, the sensor. Or it could be a local server sitting in a factory or an office building. Or even a regional gateway that aggregates data from multiple nearby devices. The crucial part is simply that it's physically closer to where the data originates. And this concept is absolutely vital for environments where these connected devices are generating truly vast quantities of data, and where traditional cloud computing, simply due to the inherent delays of network transmission, what we call latency, just isn't optimal for the speed of response that's needed.
Okay. So for you, our listener, what does this decentralization really mean in practical terms? How does it stack up against that centralized cloud model that, as you said, has dominated our digital lives for so long? Because like I mentioned, the cloud is almost synonymous with, massive scalability and seemingly boundless processing power.
Well, it represents a fundamental architectural shift, definitely. But it's important to see it as a symbiotic relationship, not really a competitive one. They work together. Centralized cloud processing remains absolutely unparalleled for its capacity for massive data storage, right? And for performing those complex, long-running analytics across enormous data sets, or identifying those overarching long-term trends. Imagine trying to train a really sophisticated AI model on petabytes of historical data, or running intricate simulations that require immense computational heft. The cloud is built specifically for that kind of workload.
Right, the heavy lifting.
Exactly. However, its Achilles heel, if you like, is that inherent need to transmit data across networks. And that inevitably introduces latency. Even with superfast fiber optics, there's still a physical distance limitation, the speed of light, that translates into measurable delays. Milliseconds count in many applications. Edge computing, by stark contrast, its whole philosophy prioritizes geographical data proximity and near instantaneous action. By processing data literally at the source, maybe on a tiny processor within a security camera itself, or on a more powerful gateway computer in a smart factory, those critical delays are drastically reduced, often down to just milliseconds or even less.
Can you give an example of where that difference is critical?
Sure, think about an industrial robot on an assembly line. If a sensor detects an immediate safety hazard, say someone's hand gets too close, waiting for that data to travel to a cloud server, get processed, and then have a stop command sent back,
Right.
well, the delay could be catastrophic.
Right.
Precisely. With edge processing happening right there, perhaps on the robot controller itself, the robot can react almost instantaneously. So again, it's not about replacing the cloud. It's about augmenting it, creating a much more efficient hybrid model. The cloud then becomes the sort of central brain for the aggregated data, for the deeper, less time-sensitive insights, and for the overall orchestration of the system, while the edge becomes the rapid response nerve endings, handling the immediate mission-critical decisions locally. This data proximity, being close to the generation point, directly translates to faster response times, which is absolutely critical for any IoT application where real-time decision-making is paramount. Think autonomous vehicles, critical infrastructure monitoring, real-time patient monitoring, the list goes on.
That distinction, that idea of having the processing power right where the data lives, it makes so much sense, especially, like you said, for those really time-sensitive applications. So, okay, when we talk about integrating edge computing, let's get concrete. What are the tangible benefits that IoT devices and applications actually gain? What real-world problems does this solve on the ground for businesses and organizations deploying these systems?
Yeah, the advantages are indeed quite compelling, and they directly address some of the biggest scaling and performance challenges we face in large-scale IoT deployments, especially as the sheer volume of connected devices just continues to grow exponentially. It's staggering, really. Perhaps the most compelling benefit, as we've sort of hinted at already, is the dramatic reduction in latency and the resulting improvement in response times.
Latency being that delay, right?
Exactly. Latency, for anyone maybe less familiar, is simply the delay between a data point being generated by an IoT device, a sensor reading, for example, and a subsequent action being taken based on that data. By processing information locally, right at the edge, organizations can achieve near instantaneous responses. Let's go back to smart manufacturing. If a sensor on a crucial piece of machinery detects an unusual vibration pattern or maybe a sudden temperature spike that indicates an impending failure, an immediate response is absolutely vital. You need to prevent costly downtime, ensure worker safety, maybe avoid producing defective products.
You can't wait for a round trip to the cloud.
Precisely. Sending that raw, often high-volume data to the cloud, even with fast networks, introduces delays that are just unacceptable for these critical real-time control scenarios. Edge computing, maybe leveraging things like lightweight containerization or specialized AI accelerators right on the device, makes it possible to detect, analyze, and act within milliseconds. And this isn't just about speed, although speed is key. It's about enabling truly autonomous and intelligent systems where every microsecond literally translates into operational efficiency or cost savings or even safety.
Okay, so speed and responsiveness, that's number one. What else?
Building directly on that, edge computing offers significantly enhanced bandwidth efficiency. And this is a huge factor, both for cost savings and for enabling scalability. Just picture a scenario, maybe a sprawling factory with thousands of sensors, or think even bigger, millions of high-definition smart cameras deployed across an entire city.
That's a mind-boggling amount of data.
It is. And if all of that raw, unprocessed data had to be continuously transmitted back to a central cloud, well, it would quickly overwhelm network bandwidth. We'd see massive congestion, and the data transfer costs would become incredibly high, potentially prohibitive.
Yeah, I can imagine the bills.
Right. So edge computing addresses this head-on by allowing for sophisticated data filtering, aggregation, and pre-processing right at the source. So instead of transmitting terabytes of raw video footage from those city cameras, for instance, an edge device located near the camera might only send a compressed snapshot or maybe just a simple metadata alert when a specific event is detected, like, say, an unauthorized person entering a restricted area or a piece of equipment exceeding a preset temperature threshold.
So it sends the important stuff, the actionable insights, not just the noise.
Exactly. Only the most critical, summarized, or truly relevant data is then forwarded to the cloud for deeper, long-term analysis or archival storage. This dramatically reduces the amount of data transmitted over those, often expensive, wide area networks. which leads to substantial savings on bandwidth costs and alleviates network congestion, making the entire IoT system far more scalable and economically viable, especially in the long run.
That makes a lot of sense. So reduce latency, better bandwidth use, any other major advantages?
Yes, and this leads us to a really crucial and actually often overlooked advantage: data sovereignty and compliance considerations.
Ah, the regulatory side.
Oh, precisely. This raises a really important question for any organization, especially those operating globally. Where is your data physically located? And who controls it? Because for many industries, think healthcare, finance, government, and in many regions, there are stringent data residency laws and compliance regulations.
Yeah.
Things like Europe's GDPR or HIPAA in U.S. healthcare.
Right, rules about where data can and cannot go.
Exactly. These rules dictate precisely where certain types of sensitive data must be stored and processed. Transferring personally identifiable information or highly sensitive operational data across international borders, or even just out of a specific regulatory zone. Well, if not handled with absolute care, that can lead to severe legal penalties, significant fines, and frankly, profound reputational damage.
So how does edge computing help with that?
Edge computing provides a powerful solution here by enabling that sensitive or regulated data to remain within specific geographical boundaries or even directly on premises within the organization's own physical and logical control. So the data doesn't necessarily have to leave the country it originated in or leave a secure corporate network just to be processed for immediate insights.
Okay, so you process it locally to meet the rules and maybe only send anonymized or aggregated data to the cloud later.
Precisely. Or only send data that isn't subject to those strict regulations. This capability significantly helps organizations meet their regulatory obligations, maintain robust data privacy for their customers or employees, and ensure ironclad data control. And that's becoming increasingly vital in our data-driven, globally connected world. It offers a layer of control and assurance that is simply much harder, sometimes impossible, to achieve when all data must reside in a centralized, potentially offshore cloud data center.
Those benefits really do paint a very compelling picture. Reduce latency, bandwidth savings, better compliance. It sounds like edge computing truly is a game changer, addressing some really fundamental challenges of scaling IoT effectively. But as you mentioned earlier, this isn't really an either situation with the cloud, is it? We're not saying goodbye to the cloud altogether.
Not at all, no.
So for organizations wrestling with these decisions, and I imagine many are, how do they determine the right mix? What's the optimal balance between edge processing and cloud computing for their unique IoT applications? This feels like it must be a deeply strategic decision, not just a purely technical one.
You've hit on the critical point there.
Yeah.
It's absolutely about finding that optimal balance. And it's definitely a nuanced conversation because, as you suspect, there's no single one-size-fits-all answer. The strategic decision-making process really hinges on carefully assessing several critical factors. You're weighing performance needs against cost implications and balancing all of that with security imperatives.
Okay, so what are those key factors?
Well, firstly, the application performance requirements are often the primary driver. What does the application actually need to do, and how fast does it need to do it? For applications that absolutely demand immediate real-time responses and ultra-low latency, the edge becomes paramount. It's non-negotiable in some cases. Think again about fully autonomous driving. Those split-second decisions about braking, steering, or accelerating, they are literally life or death situations.
There's zero room for delay.
Zero. You simply cannot afford even a few milliseconds of delay, sending critical sensor data to a cloud server, waiting for processing, and then receiving a command back. It just wouldn't work. The decision-making logic, often powered by sophisticated AI models that have been specifically optimized for edge deployment, has to reside right there in the vehicle itself. Conversely, though, for applications that require vast historical data analysis, or maybe long-term pattern recognition across massive datasets, or extremely compute-intensive AI model training, the centralized cloud remains the superior choice. It has the scale.
Right, the training versus the execution, perhaps.
That's a great way to put it. So, for example, while that self-driving car processes its real-time driving decisions at the edge, the petabytes of aggregated, often anonymized, driving data collected from an entire fleet are typically uploaded to the cloud for training the next generation of AI driving models. That training is a massive batch process. It doesn't demand real-time interaction, and it allows the cloud to leverage its immense, scalable compute resources effectively. So the cloud remains the powerhouse for that big data analytics over extended periods and for developing the core intelligence that is then perhaps refined and deployed out to the edge devices.
Okay, performance needs are key. What's next on the decision list?
Next, inevitably, are the cost considerations. And this is not always as simple or straightforward as it might seem initially. While edge computing can indeed significantly reduce those data transmission costs to the cloud by pre-processing and cutting down bandwidth consumption.
Which sounds like a win.
It is, but it introduces new costs. You have the capital expenditure, the upfront cost for the edge hardware deployment. You're buying servers, gateways, ruggedized devices. Then there's the ongoing maintenance, the power consumption, and the operational management of these geographically distributed edge devices. You are essentially buying, deploying, and maintaining physical infrastructure, sometimes on-site, sometimes across various remote locations. And that can be a significant upfront investment and also an ongoing operational burden.
Compared to the cloud's model.
Right. The cloud, on the other hand, offers that incredible flexibility and an on-demand pay-as-you-go model. It allows organizations to scale resources up or down almost instantly and theoretically only pay for what they actually consume. However, continuous high-volume data egress that's moving data out of the cloud and the long-term storage of massive data sets can quickly accumulate significant operational costs over time in the cloud as well.
So it's a trade-off.
It's absolutely a trade-off. Organizations need to meticulously analyze the total cost of ownership, the TCO. They have to carefully weigh that initial capital expenditure for edge infrastructure against the ongoing operational expenses of cloud services. This really requires a detailed financial model that considers things like anticipated data volumes, the processing needs at edge versus cloud, the expected lifespan of the edge infrastructure, and critically, the staffing required for ongoing maintenance and support of that distributed system.
That sounds complex. Performance, cost. What's the third pillar?
Finally, and this is arguably becoming the most critical factor in many discussions, we must deeply consider the security implications.
Right, you mentioned the distributed nature earlier.
Exactly. If we connect this to the bigger picture, distributing processing power out to the edge inherently distributes your security perimeter. It shatters the old model of a single defensible castle wall. This can significantly increase the attack surface because there are now potentially thousands or even millions of individual devices and network points spread across diverse, often less physically controlled, locations that all need to be secured.
More doors and windows to protect.
A perfect analogy. Now, centralized cloud providers, they invest massively in robust security measures. They have dedicated world-class teams protecting their data centers, employing sophisticated defenses. But even there, a single point of failure or a really sophisticated breach in the cloud could potentially have wide-ranging impacts across all of its customers. The unique challenge with Edge, though, is securing those potentially disparate devices. They often have varying hardware capabilities, maybe running different software versions. They might have different physical vulnerabilities depending on where they're deployed. Ensuring data integrity right at the edge, securing the communication channels between all the edge devices and between edge and cloud, and protecting against physical tampering, especially for devices deployed in remote or publicly accessible areas. These are all monumental security tasks.
It sounds like it requires a whole new security mindset.
It absolutely does. It demands a comprehensive, multi-layered security strategy that spans the entire IoT ecosystem, from the tiniest sensor all the way up to the central cloud platform. It has to encompass meticulous attention to device identity and authentication, robust encryption for data, both when it's stored on the device, at rest, and when it's being transmitted in transit, secure boot processes to prevent malware loading during startup, and crucially, continuous vulnerability management and monitoring across the entire distributed infrastructure. It's a constant vigilance requirement.
Okay, those factors, performance, cost, security, really highlight the complexity involved in designing and building a truly robust hybrid edge cloud IoT system. Theory is one thing, but like we said, real-world applications often speak louder than any explanation. Could you walk us through some compelling case studies, some actual scenarios where edge computing isn't just a concept on a whiteboard, but something that's truly shining and making a tangible difference in the world of IoT today?
Absolutely. And these examples, I think, powerfully illustrate the tangible benefits and the truly transformative potential of edge solutions across a whole range of vital industries. Let's start with smart manufacturing and predictive maintenance, as we touched on earlier. In a modern, highly automated factory, you might have thousands, sometimes even tens of thousands of sensors. They're monitoring every conceivable parameter, vibration, temperature, pressure, electrical current, acoustic signatures, all coming from critical machinery like robotics arms, CNC machines, conveyor belts, assembly lines.
A constant stream of data from everywhere.
An absolute flood. Now, historically, maybe some of that raw sensor data might have been sampled and sent to a central system, perhaps in the cloud, for later analysis. But with edge computing, specialized edge devices, they could be industrial PCs, gateways, even embedded systems are deployed directly on the factory floor, often integrated right into the machinery itself or positioned very close by in local control cabinets. These edge devices possess the necessary computational power to process this high-volume sensor data in real time, right there where it's being generated.
So they analyze it on the spot.
Exactly. They can detect subtle anomalies or deviations from normal operating parameters, for instance, a slight, almost imperceptible change in the vibration signature of a motor that indicates early bearing wear is starting. Or maybe a gradual but concerning increase in the operating temperature in a critical component. Instead of transmitting terabytes of raw, often noisy data up to the cloud, the edge device processes it locally. It might apply machine learning algorithms trained specifically for that machine's normal behavior, and it flags potential issues immediately.
Before the machine actually fails.
Precisely. This enables true predictive maintenance. It allows the maintenance teams to schedule repairs before a machine breaks down unexpectedly. And the impact of that is huge. It dramatically reduces unplanned downtime, which, as you can imagine, can be incredibly costly in terms of lost production, idle labor, potentially missed delivery deadlines. It fundamentally optimizes operational efficiency by ensuring machines run longer, more reliably, and only receive maintenance precisely when they need it, not too early and certainly not too late.
That's a powerful example. What about other sectors?
Okay, let's shift gears and consider the profound impact edge is having on smart grids for energy management. Our modern energy grids are becoming exponentially more complex, aren't they? They're no longer just about those big, centralized power plants distributing electricity out in one direction. Now they have to integrate diverse and often intermittent renewable sources like solar and wind power. They have to deal with constantly fluctuating demand from millions of consumers, electric vehicle charging, and so on. And all while needing to be incredibly resilient against disruptions, whether from weather or equipment failure.
A much more dynamic and fragile system in some ways.
Very much so. Edge computing is now being deployed quite extensively in electrical substations, at key distribution points across cities and towns, and even within individual smart meters installed at homes and businesses. These edge devices, they could be sophisticated controllers or sensors, actively monitor and manage energy flow locally in their specific part of the grid. They can respond to changes in energy demand or supply in real time. For example, they could automatically reroute power around a fault that's detected in a local segment of the grid to minimize the number of customers affected by an outage. Or they can help balance electrical loads across different feeders to prevent overloads during peak demand periods, maybe by slightly adjusting voltage or encouraging demand response programs. They can even automatically isolate a fault to contain its impact and prevent cascading failures.
So they're making the grid more self-healing and stable.
Exactly. This vastly improves grid stability, overall operational efficiency, and resilience against disturbances. It helps ensure a more reliable and ultimately more sustainable power supply for everyone. And the speed of decision-making right at the edge is absolutely critical here for preventing widespread blackouts or brownouts in this increasingly complex grid environment.
Okay, manufacturing, energy. What about something maybe closer to our everyday lives?
Well, what's truly fascinating, and something many people interact with daily without perhaps realizing the edge component, is the application within connected vehicles, and particularly autonomous driving. A modern connected vehicle is, in essence, a highly sophisticated mobile edge device. It's a data center on wheels, practically.
It's all those sensors.
An incredible array. They're equipped with cameras providing 360-degree visual data, radar systems for measuring distance and speed of surrounding objects, LiDAR for creating detailed 3D maps of the environment, ultrasonic sensors for close proximity parking maneuvers, GPS, inertial measurement units. The list goes on. And all these sensors are collectively generating terabytes of data every single hour of driving.
Terabytes per hour. Wow.
It's staggering. Now, for autonomous driving functions, even advanced driver assistance systems, let alone full self-driving critical decisions like collision avoidance, maintaining lane position, or navigating complex urban intersections demand absolutely instantaneous processing. As we discussed, there is simply no permissible time, no margin for error, to send this massive real-time stream of sensor data up to a distant cloud, wait for it to be processed, and then receive an instruction back to, say, apply the brakes or swerve.
The physics just don't allow it.
Precisely. That delay, even just tens of milliseconds, could be catastrophic in a dynamic driving environment. So, edge computing specifically, Powerful onboard processors, often with integrated AI accelerators, designed for neural network inference, processes this torrent of sensor data locally, right inside the vehicle, to make those real-time driving decisions. The car effectively thinks and reacts on its own, based on its immediate surroundings.
So where does the cloud fit in for cars then?
The cloud, in this very sophisticated hybrid scenario, is typically reserved for the less time-sensitive but still vital tasks. Things like downloading over-the-air software updates to improve the car's features or driving algorithms. Continuously updating the high-definition maps that the navigation system relies on. For fleet operators, like trucking companies or ride-sharing services, the cloud handles long-term fleet management, analyzing efficiency, optimizing routes based on historical data. And crucially, the cloud is where those incredibly complex AI driving models are trained, using the aggregated, anonymized data collected from thousands or millions of vehicles driving billions of miles across all sorts of conditions.
So the edge handles the driving, the cloud handles the learning and updating.
That's a very good summary. This powerful hybrid approach allows for the immediate safety-critical actions needed for driving, while still leveraging the boundless resources of the cloud for long-term intelligence gathering, continuous model improvement, and overall system orchestration and updates.
Those use cases really do bring the concept to life in a way that's incredibly compelling. Manufacturing efficiency, grid stability, vehicle safety. It's clear the transformative potential of edge computing is enormous across so many vital sectors. But, as with any powerful and complex technology, there must be significant hurdles, right? It can't possibly be a completely smooth road to deploying these sophisticated edge solutions widely. No solution comes without its challenges, and these sound like really intricate systems to build, manage, and, as you highlighted, secure.
You are absolutely right. There's no free lunch here. While the benefits are clear and highly compelling, implementing edge computing within existing, and even new, IoT frameworks present several significant technical challenges. And organizations really need to meticulously plan for and address these challenges. Without proper foresight, robust strategies, and often specialized expertise, these hurdles can quickly become quite formidable, potentially derailing projects.
Okay, so what are the big ones? What keeps implementers up at night?
Well, one of the primary and often seriously underestimated challenges is dealing with connectivity issues. Ensuring consistent and crucially reliable network connectivity for all these edge devices is absolutely paramount for most applications. But it's often very difficult to guarantee. Think about where these devices might be located. They could be in incredibly diverse and challenging environments. Remote agricultural fields where cellular coverage is spotty or non-existent. Maybe harsh industrial environments full of heavy machinery causing electromagnetic interference that disrupts wireless signals. Or even in basements or moving vehicles where internet access might be intermittent or completely unavailable at times.
So you can't assume they're always online.
You absolutely cannot. Maintaining robust communication channels, not just between the edge devices themselves, maybe they form a local mesh network of sensors, but also, critically, between those edge devices and the central cloud infrastructure, can be incredibly difficult. This includes navigating wildly varying network speeds. You might have high bandwidth fiber in one location and very slow, low power, wide area networks, LPN, designed for minimal data in another. You have to deal with significant bandwidth limitations in many remote locations, and you need to ensure absolute data integrity during transmission, especially in scenarios where reliable internet might not always be consistently available. You need mechanisms for buffering, retries, ensuring data isn't lost.
So you need the edge device to be smart enough to handle being offline.
Precisely. A key design challenge is enabling edge devices to continue operating autonomously, or at least semi-autonomously, to a certain degree when they lose connection. They need to be able to store data locally, perhaps perform critical functions based on local processing, and then intelligently sync up with the cloud when connectivity is eventually restored. And that adds another significant layer of architectural complexity to the whole system.
Okay, connectivity is a big one.
Well,
What else?
Next, consider the sheer monumental task of device management and updates at scale. If an organization is deploying hundreds, thousands, or potentially even millions of edge devices across a wide, dispersed geographical area, think smart meters across a city, sensors along a pipeline, or devices in a global retail chain. Just managing that vast, heterogeneous ecosystem becomes an operational challenge of immense scale. It's daunting.
Just keeping track of them all sounds hard enough.
It is. And it involves everything from the initial provisioning and configuration, securely getting each new device set up with the correct software image, network settings, security credentials, and operational parameters, to then securely deploying critical software updates and security patches remotely, often over the air. It involves continuously monitoring each device's health and performance. Is it online? Is it functioning correctly? Are its resources being overtaxed? And it involves efficiently troubleshooting issues, ideally without needing to send a technician out for a physical site visit, which is often impractical or prohibitively expensive.
Rolling trucks costs a lot of money.
Exactly. Imagine the logistical nightmare, the cost of having to physically visit thousands of devices just to apply a critical security patch or diagnose a recurring problem. That's simply not scalable or economically feasible in the long term. So, effective remote management, ensuring that all devices are consistently running the correct, secure software versions and doing this reliably across a geographically dispersed and highly diverse hardware ecosystem, which, remember, often involves devices from multiple different vendors, running different operating systems, possessing vastly varying computational capabilities. This is a significant operational challenge that absolutely requires sophisticated device management platforms and highly automated processes. There's no way to do it manually at scale.
Connectivity management. And you mentioned security before. Let's circle back to that.
Yes, and it ties directly into management. This raises that incredibly important question that demands meticulous ongoing attention. Security vulnerabilities. How do you effectively secure this vastly distributed network where your compute power, your data processing, and your potential points of entry are now scattered across potentially thousands or millions of individual endpoints?
The attack surface just explodes, right?
It absolutely explodes. The expanded attack surface created by the sheer number of edge devices makes them inherently attractive and potentially more vulnerable targets for cyber attacks compared to a centralized cloud. Each edge device, regardless of its size or function, whether it's a tiny low-power sensor or a powerful gateway server in its communication pathways back to the cloud or to other devices, represents a potential vulnerability point that attackers can probe. And unlike those heavily fortified, physically secure, centralized cloud data centers with their dedicated 247 security teams, edge devices can sometimes be physically accessible to malicious actors, especially if deployed in public or remote areas. They might have limited processing power, making it hard to support complex encryption algorithms or run robust security agents alongside their primary functions. And they can be much harder to continuously monitor in real time compared to centralized servers.
So security needs to be built in from the start, not bolted on.
Absolutely critical. Organizations must implement incredibly robust end-to-end security measures across the entire life cycle of these devices, from the moment they're manufactured and provisioned, through their operational life, right up to their eventual secure decommissioning. This includes enforcing strong, ideally hardware-backed device identity and multi-factor authentication to ensure only authorized devices and users can access the system. It means implementing stringent encryption for data, both when it's stored on the device at rest and when it's being transmitted over any network in transit. It involves leveraging secure boot processes to ensure the device only loads trusted, untampered software during startup. And as mentioned, it requires deploying continuous monitoring solutions, intrusion detection systems, log analysis to detect and rapidly respond to threats across the entire sprawling edge infrastructure. This is absolute critical, not just for protecting sensitive data, but for maintaining the operational integrity of the system and preventing unauthorized access or manipulation that could lead to devastating real-world consequences in critical infrastructure, smart cities, or industrial control systems.
Okay, those are indeed substantial hurdles. Connectivity, management at scale, and that pervasive security challenge really underscore the complexity involved here. So for the developers and the technical teams out there who are looking to tackle these challenges head on, who need to build out these robust edge solutions, what kinds of frameworks and tools are currently available to help them? Are there established platforms or, best practices they can lean on to help navigate this increasingly complex landscape without reinventing the wheel every time?
That's a great question, because the good news is the ecosystem for edge computing is indeed rapidly maturing. It's moving fast. And fortunately, it now offers a growing array of really powerful platforms and specialized development tools, specifically designed to simplify the entire development and deployment lifecycle for edge applications. This progress is making edge computing far more accessible to a broader range of organizations, even those that might not possess deep, highly specialized embedded systems expertise in-house.
So what do these platforms look like? Are they extensions of the cloud platforms many are already using?
Yes, in many cases, that's exactly what they are. We're seeing the rise of several popular edge platforms that fundamentally extend the familiar capabilities and management paradigms of the leading cloud providers much closer to the physical edge. This makes it significantly easier to manage and deploy applications consistently across that entire continuum, from the cloud down to the device. For example, you have Azure IoT Edge, which is Microsoft's primary offering in this space. It essentially allows developers to containerize and deploy cloud services, things like pre-trained Azure AI models for inference, sophisticated stream analytics modules, or even custom business logic written as functions directly onto edge devices.
So you build it in Azure, deploy it to the edge.
Pretty much. It means your edge devices can intelligently act on data generated locally in real time without constantly needing to rely on the cloud for every bit of processing. Yet critically, they remain centrally managed, monitored, and updated right from your familiar Azure Cloud portal, providing that seamless operational bridge. Similarly, AWS Greengrass is Amazon's equivalent service, designed specifically to extend core AWS functionality out to edge devices. It enables you to run things like AWS Lambda functions, which are those pieces of serverless code that execute on demand, without you having to manage the underlying servers perform local messaging between devices using MQTT and cache data locally. And crucially, Greengrass allows devices to operate even when disconnected from the internet, continuing to run local logic and process data, and then automatically syncing back up with the AWS cloud when connectivity is restored, uploading processed data or receiving new deployment instructions or configurations.
So these platforms handle a lot of that complexity we talked about, deployment, management, offline operation.
They aim to abstract away a significant portion of it, yes. They are incredibly powerful because they bring that familiar, often more streamlined, cloud development experience directly to the edge environment. They handle much of the underlying complexity of managing individual, distributed devices, dealing with intermittent connectivity, and deploying applications securely and consistently.
Okay, those platforms sound key.
Mhm.
What about the actual coding? What languages and tools are developers using?
Right, in terms of programming languages and development tools, building for the edge often requires proficiency in languages that are well suited for both the constraints of embedded systems and the demands of real-time processing, as well as those languages commonly used for cloud integration and data science. It's often a blend. Languages like Python are incredibly popular right now. That's partly due to their versatility, their rich ecosystem of libraries for data manipulation and communication, but especially because of their widespread use in the machine learning and AI world. It's relatively easy to take models trained in the cloud using Python frameworks like TensorFlow or PyTorch and deploy them for inference on edge devices using tools like TensorFlow Lite or ONNX runtime.
Makes sense, given the AI focus. What about more traditional embedded languages?
Absolutely. For performance-critical applications, especially on more resource-constrained hardware where every CPU cycle and byte of memory counts, languages like C and C++ are still often the go-to choices. They offer that granular control over system resources needed for real-time operating systems or bare metal programming. We're also seeing significant traction for JavaScript, particularly with Node.js, on slightly more powerful edge devices or gateways. Its asynchronous, event-driven architecture is actually exceptionally well suited for handling IoT messaging protocols like MQTT and processing streams of incoming sensor data efficiently. And the development tools available today aim to facilitate the entire lifecycle. You have integrated development environments, IDEs, with plugins for edge development. You have the specialized software development kits, SDKs, provided by the cloud vendors like Azure and AWS, tailored for their platforms. Plus, you have crucial tools for containerization like Docker, which allows applications and their dependencies to be packaged up and run consistently and portably across different edge hardware configurations. And orchestration platforms like Kubernetes, often using lightweight distributions like K3s or micro K8s, are increasingly being used to manage containerized applications across clusters of edge devices.
So lots of tools evolving to support this. What about community help? Is there support out there?
Yes, and that's incredibly important. Community resources and support channels are absolutely vital for anyone venturing into this space, especially given how quickly it's evolving. Edge computing is still a relatively new and rapidly changing field compared to, say, traditional web development or even cloud computing. So strong community support is invaluable for both seasoned professionals trying to keep up and for newcomers trying to get started. Developers can leverage a really wealth of open source projects. These often provide ready-to-use software components, common communication libraries, reference architectures for specific use cases, and practical examples that can significantly accelerate development and avoid common pitfalls. Beyond code, you have online forums like Stack Overflow tagged sections or vendor-specific community forums, extensive technical documentation provided by the platform vendors, which is usually very good, and vibrant online developer communities on platforms like GitHub or Discord. These are essential places for sharing knowledge, troubleshooting tricky issues because you will encounter them, and staying updated on the very latest best practices, security advisories, and emerging technologies in the edge space. This collective knowledge base is truly essential for navigating the inherent complexities of edge deployments and for accelerating innovation, ensuring that developers aren't constantly reinventing the wheel, but can build upon established, community-vetted solutions and patterns.
That's great to hear that the ecosystem is maturing with platforms, tools, and community support. Okay, we've covered the fundamental concepts, we've explored the really compelling benefits, we've delved into the significant challenges which are not trivial, and examined the powerful tools available today. It's been a truly comprehensive look at the current landscape. So, as we look towards the horizon now, what lies ahead for this exciting intersection of technologies? What anticipated trends and major innovations should we as listeners be watching for at the convergence of IoT and edge computing? Where is all of this transformative technology heading next?
Yeah, the future of this integration is, I think, incredibly promising.
Yeah.
It's really poised to unlock entirely new capabilities, things that will reshape not just specific industries, but potentially our everyday interactions with technology and the physical world all around us in quite profound ways.
Okay, intrigue us. What's coming?
Well, a major trend that we're already witnessing the strong beginnings of, and which I believe will only accelerate dramatically in the coming years, is the much deeper integration with artificial intelligence and machine learning, specifically what's increasingly being called AI at the edge.
Hmm.
So instead of the older model of sending all that raw sensor data up to the cloud for AI model inference, using a pre-trained AI model to make predictions or decisions based on new data, these powerful AI models can now be significantly compressed, optimized for efficiency, and deployed directly onto surprisingly resource-constrained edge devices, even tiny microcontrollers in some cases.
So the AI thinking happens right on the device itself.
Exactly. This enables real-time, highly intelligent decision-making without needing constant cloud connectivity or suffering the associated latency penalty. Imagine, for example, a smart security camera that can perform complex tasks like facial recognition or sophisticated anomaly detection, like identifying unusual movement patterns, directly on device. It could instantly alert security personnel to a potential intruder without having to stream terabytes of high-definition video up to a distant data center for analysis. Or picture a manufacturing machine on a production line that can identify subtle product defects using AI-powered computer vision, maybe detecting microscopic cracks or color variations right there on the line itself, without any network delay whatsoever, allowing for immediate rejection or correction.
That sounds incredibly powerful for automation.
It is. This innovation fundamentally pushes intelligence and autonomous decision-making capabilities much closer to the source of the data. It makes systems far more autonomous, much more responsive, and considerably more efficient, especially in environments where network connectivity might be unreliable or where bandwidth is severely limited or expensive. It's truly about bringing the brain of the system much closer to the eyes and ears, the sensors of the system. AI at the edge. Got it. What else is driving the future here? Well, if we connect this to the bigger picture of network infrastructure, the rapid growth and ongoing evolution of 5G networks and eventually 6G, and their profound impact is perfectly complementary to the continued evolution and adoption of edge computing. They really go hand in hand. 5G's foundational characteristics, its promise of ultra-low latency down into the single-digit milliseconds, its massive bandwidth capabilities, and its remarkably high connection density, supporting potentially millions of devices in a square kilometer. These are precisely the enablers that many sophisticated edge applications need to truly thrive and reach their full potential.
So 5G makes edge even better.
It significantly enhances the possibilities, yes. The ultra-low latency of 5G will facilitate even more responsive edge applications, enabling near-instantaneous data transfer between edge devices and local edge servers, almost as if they were directly wired together, even over a wireless link. This is critical for things like real-time remote control of robotics or tactile internet applications. Its massive bandwidth capabilities will seamlessly support the transmission of large volumes of pre-processed data or high-definition video feeds from the edge up to the cloud when deeper analysis or archival is required, or maybe between various edge nodes for collaborative intelligence sharing. And its high connection density means it can reliably handle those vast deployments of IoT sensors and devices, simultaneously think massive sensor networks in smart cities or agriculture, without succumbing to the network congestion issues that plague older cellular technologies.
So what kind of new applications might this unlock?
Well, together, 5G and edge computing are already beginning to unlock use cases that were previously impossible or impractical due to network limitations. Think about highly immersive augmented reality, AR, or virtual reality VR applications that require instant data processing and rendering for realistic holographic overlays onto the real world that needs edge compute very close by, connected via 5G. Or imagine those vast networks of interconnected smart city sensors we talked about that can collaboratively coordinate traffic light timings based on real-time flow, or dynamically manage waste collection routes or monitor environmental conditions, all adjusting instantly to changing conditions thanks to edge processing and 5G connectivity.
Okay, AI at the edge, supercharged by 5G. What's the final piece of the future puzzle?
The final piece, and it's crucial for widespread adoption and avoiding fragmentation, is the ongoing development of evolving industry standards and interoperability initiatives. As edge computing continues to mature and expands its footprint across more and more industries and applications, the need for common, agreed-upon industry standards will become increasingly critical. Right now, the landscape can still feel somewhat fragmented. Different vendors often offer excellent, but sometimes proprietary solutions that don't always play well together easily. Integrating devices from vendor A with a platform from vendor B can sometimes be a significant engineering challenge.
The classic vendor lock-in problem.
Exactly. So the future really requires, and we're seeing movement here, standardized protocols for device communication. Beyond just MQTT, maybe more domain-specific ones. Common data formats and semantic models for seamless information exchange so the devices and platforms understand each other, and robust platform interoperability APIs across diverse vendor ecosystems. These standards will be absolutely crucial. They will enable truly seamless integration across diverse vendors and technologies, which will, in turn, significantly reduce that vendor lock-in risk for organizations adopting these technologies. It will also simplify development efforts by providing common building blocks, reusable components, and standardized APIs for developers to target. And ultimately, it will accelerate the widespread adoption of edge solutions by fostering a much more cohesive, competitive, and truly collaborative ecosystem. Imagine a future where, ideally, any IoT device, regardless of its manufacturer, can effortlessly and securely connect and share meaningful data with any edge platform or application, enabling a truly plug-and-play experience for a much broader range of transformative applications. That's the goal.
Wow, this has been an incredibly insightful and really detailed exploration into how edge computing is truly shaping and, frankly, defining the future of IoT. It's absolutely clear that by intelligently harnessing its power, organizations can unlock vastly better performance, achieve that critical ultra-low latency, and dramatically improve data management, security, and compliance across their entire connected ecosystems. It really does feel like it's not just an incremental improvement over pure cloud, it's a fundamental shift in how we need to think about architecting systems to process the sheer deluge of data generated by our increasingly interconnected world.
Absolutely. I couldn't agree more. And for you, our listener, if you're a developer working in this space, understanding the technical nuances and the practical implementation strategies of these edge solutions, everything from selecting the right hardware and platforms to robustly securing these diverse distributed devices, that knowledge is becoming absolutely crucial for building the next generation of successful IoT applications. And for those in technical management or leadership roles, truly leveraging this in-depth understanding to drive innovation within your teams, to optimize your organizational strategies, and to make those informed long-term architectural decisions. Well, that's going to be key to maintaining competitiveness and achieving future success. The central takeaway, I think, is profound and worth repeating. The forthcoming era of truly intelligent, truly responsive IoT solutions absolutely hinges on effectively and strategically balancing the boundless historical analytical power of cloud resources with the immediate, localized, and real-time processing capabilities offered by edge computing. It is in essence about designing and deploying distributed intelligence for an increasingly distributed and data-rich world.
So, thinking about that distributed intelligence, what does all of this ultimately mean for you? As edge computing continues its relentless march, bringing intelligence and sophisticated decision-making capabilities ever closer to where data is actually generated, enabling increasingly autonomous systems that can sense, reason, and act independently and in real time, right there in the physical world. Consider this. What entirely new frontiers of human technology interaction might be unlocked when our everyday devices are not just passively connected but inherently intelligent and context-aware? And perhaps even more intriguingly, what novel, maybe completely unexpected applications and societal shifts might emerge from this increasingly decentralized intelligence, transforming aspects of our work, our cities, our health, and our lives in ways we can perhaps barely even imagine today?
It's certainly a lot to ponder, and the implications, as you say, stretch far beyond just technical efficiency into potentially profound societal impacts, both positive and perhaps challenging. But hopefully this deep dive today has given you a solid, comprehensive foundation for understanding this truly transformative technology and its profound ongoing impact.
We deeply encourage you to continue exploring this fascinating world of edge computing further. What aspects truly stood out to you? What questions does it raise for your own work or interests? We hope this deep dive helps you feel genuinely well informed and better equipped for the increasingly intelligent future that's rapidly unfolding around us.